Okay, let's see. Let's go ahead and get started, okay? I think it will record the audio. It is picking up the audio here, but it's maybe it's just a little bit faint. Hopefully it'll be okay. All right, let's go ahead and get started. So I want to start by introducing you guys to a medical imaging process called thresholding. Okay, so and I'm going to show you guys that here in Matlab. Okay, so I just wrote some code here in Matlab, um, and I'm going to bring in an image. I'm going to use the imRead function to bring in this hand.tiff. This is an X-ray image of a hand. Okay, and I'm gonna call it img for image, and then we're gonna look at it using the imTool function. Okay, so I'll run that, and let me make this a little bit bigger. Okay, so here's an X-ray image of the hand. Okay, and again, if you recall, an image, if we take a closer look at this image, okay, recall that an image is nothing but a matrix of pixels, right? Here you can see the individual pixels as I move this box around, right? Okay, and if I zoom in on it, you can see that the pixels are really just a bunch of numbers, okay? And where it's brighter is a higher number, and where it's darker is a lower number. Okay, see, okay, as I move around, see I'm in a dark region of the image. You see it has low pixel values, around 40 or 50 or 60. If I move this around over to a brighter spot of the image, okay, where the bone is, okay, you'll see that the pixel values are now higher, like 150, 140. Okay, so and that's because different tissue have different attenuation coefficients, right? And so it's going to attenuate, bone will attenuate more than soft tissue. But because we look at the negative, right, we reverse it, the bone appears brighter, okay, in the digital representation of that image, right? Okay. So let's take a look at a profile of this image. Okay, so if I look at a profile, so I'm going to click once here and drag a line across here, okay, and let's look at this profile, okay. So what has been plotted here, this is the x-axis on the on the image, right? Or the number of columns. So columns go across this way, rows go down, okay? So this is the number of columns, okay? And this is the intensity of each pixel at that particular location at that column, okay? And I drew a line across right here, right? Okay, so the pixels right here at the beginning are darker, That's why they are about 30 or 20 pixel value of 30 or so. That's background. Okay. Then over here, as I get into soft tissue and get into bone, you can see that the pixels are brighter. Okay, about 150 or 160, and then when I get into about here, it gets dark again, and then I reach the other bone, and it gets bright again. Can you see that? Can you guys visualize and understand what we're looking at here? We're essentially just plotting the intensity, the pixel values along one row across all the columns. Okay, where this is the first bone, this is the second bone. Okay, so thresholding is a technique where we use a cutoff value. Say we want to identify just the bone. Okay, say we want to examine just the bone. For example, in a DEXA imaging, they want to measure the bone mineral density, right? They need to identify and isolate just the bone. Okay, so you can use a technique called thresholding. So if we use some cutoff value, maybe somewhere around here, okay, maybe about 60 or 70 or so, a cutoff value right here. Let's take a look at what would happen to the image. Okay, and the way this cutoff value is going to work is that everything, all the pixels that are greater than this cutoff value, this threshold, is going to turn white, and everything below it's going to turn black. It's going to create a binary mask. It's going to create a binary image where black is 0, white is 1. Okay, so let's take a look at that. Oh, but before I do that, let's take a look at a histogram real quick of the image. Okay, so here's a histogram of the image. Okay, remember a histogram on the x-axis, these are the pixel values. Okay, remember they range from 0 to 255, where 255 is white and 0 is black. Okay, and this histogram displays the frequency. Okay, so there are 3,000 pixels in that image that are this pixel value, which is probably about 20 or so. It's dark. Okay, and these are the bright pixel values, and this is how many there are. And this produces a bimodal histogram. Okay, it's bimodal because you can see these two peaks. Okay, any idea what those two peaks are? These are the brighter pixels. Okay, the pixels that are closer to 150, and these are the brighter pixels, and these are the darker pixels. Okay, it's just another way to look at, if I cut this, you cut a threshold right about here, I would keep only the brighter pixels. The brighter pixels are the bone. Say we wanted to isolate the bone, we could use a thresholding and threshold this image and isolate the bone. So let's do that. And I've already, if you were doing this on a image that you've never used before, you could look at the histogram and get an idea where the threshold could be. You can look at a line profile and get an idea where the threshold could be. And then it'd be a trial and error process, okay, where you play with a couple of different threshold values and see how it looks. In this case, I've already done it, and I've determined that a pixel value greater than 68 produces a nice image. So here's my threshold, where all the pixels greater than 68 are going to turn white, and everything below it's going to turn black. It's going to create a mask, okay, or a binary image that looks like this. Okay, so this is where all the bone is in the image. Okay, but it's not perfect, right? Look at there are some holes here in the finger. There are holes in the finger that shouldn't be there, uh, and that's because the pixel values right there went below 68. Okay, so thresholding is not perfect. Okay, uh, I'm going to use a technique where I'm going to fill the holes. Okay, so I just use this command where I am fill, and it'll fill some of those holes. Okay, if you take a look at it, you can see that those holes are now filled. Okay. Also, you might see some other errors, like up in here. There's a bright spot here, which is bone right there where there shouldn't be any bone, because the pixel value was greater than 68 at that point. So little things like that I'm going to um, remove. Okay, using this function to remove any small blobs. Okay, then I'll use another function to detect the perimeter. Okay, to outline the edge of the image. Okay, so that one removed those little blobs that shouldn't have been there. And then I'm going to use this edge detection function to detect the edges. Okay, so here's an outline of the bone. Okay, it's kind of thin, so I'm going to use another function called IMDilate to dilate it or to make it thicker. Okay, it's just going to thicken it up a little bit. Okay, so I just make it a little bit thicker, and then I'm happy with this. Okay, it's a little bit easier to see. Okay, so that's the outline of the bone. Then I'll use another function to overlay it on top of the original image. Okay, and so here you see something that looks similar to what the DEXA imaging system have produced, right? We can identify the bone, and we can now calculate the average pixel value density of the bone, and we can calculate the area, and things like that. Okay, we can do this more further and identify the soft tissue. So I've already done this. I've looked at another threshold value. Let me show you this other threshold value. Okay. So you by shifting the threshold, okay, to everything greater than 31, okay, I'm able to get the outline of the hand. Okay, but of course the hand doesn't have these little holes, and these little white spots out here are not part of the hand, and so I can do some image processing to remove some of those noises, right? One of the image processing I'm going to do is this IMFill. That's going to remove any holes. Then I'll use the BW area open to remove any blobs that are less than 500 pixels together. And then I'm going to dilate it and smooth it out and use this edge detection function. And let's see what it looks like. Okay. Okay, so here I've identified and outlined the soft tissue. Okay, the hand. Okay, and if you are interested in learning more about this, I'll go into more detail about this in my summer class. So I'll be teaching a class in the summer over medical image processing. And we'll go through this step by step, and we'll talk about each function step by step in that class. Here I'm just giving you guys a quick overview, okay? So you don't need to be able to do this programming right now, okay? And if I want to overlay the hand, I can do that. Overlay the trace of the hand, I can do that. I'll show you. So here I've outlined the soft tissue in this image. Okay, and if I want to combine both of those and overlay the identified bone and the identified soft tissue, I can do that as well. Okay, so here, so this is what we call computer vision. Okay, so teaching a computer to identify different parts and different features in an image and segment those features using simple thresholding. So this is called image segmentation, okay, where we segmented out the bone and we segmented out the soft tissue, and we did it using thresholding. And then we did some cleaning up of the image as well to remove some of the noise in the image, right? Okay, so also remember this image right here is just a 2D signal, okay? When I draw the profile, let me see if it'll let me draw the profile. When I draw this profile, let me back up here. I draw a profile across this part right here. This is like looking at the 1D signal of the image, okay? This is just looking at one row. It looks just like an audio signal, right? Like a voice signal. So an image is really nothing but a 2D signal, right? Where you have rows and columns. So a lot of the processing that's done in signal processing can be done in image processing, just doing it in 2 dimensions. Okay. Okay, so that's a technique called thresholding. Okay, and I just want you to have a basic understanding of what is thresholding. You should understand that it's a cutoff value where everything above it it'll turn on, and everything below it it'll turn off. Okay, and by inspecting the histogram of the pixel values, you can find and isolate different parts of the image. Okay, that's what I expect you to know about that. Okay, so let's move on now and talk about. Let me show you guys some sinograms and image reconstruction of some sinograms. Okay, to do that, I'm going to create a simple image. Okay, this is the image that I created. It has just one object in it. Okay, and if I remember that if this was inside maybe the body, and I wanted to image what's in, or create a map of what's inside without cutting it open, I could create a map of this by taking projections from multiple angles all the way around and then reconstructing those projections, right? So let's take a look at what these projections would look like, okay? And the projection is done using this function called the radon function, okay? So I'll take the first projection here at theta equal to 0, okay? And this should make sense to you, okay? Because right down the middle here is, okay, right down the middle here on the x-axis are the S detectors. And in the middle is where S equals 0, right? And on this side that goes positive, and this going left goes negative, right? Okay, and so if you look at this projection, okay, so this is, so in this situation, I believe the X-rays are coming from the top, coming down, and the detectors are down here, okay? And these are the detectors. You see that they're all 0 right here, where the image is black all right here. But they start to, the projection starts to pick up some signal, some intensity, as it goes through this object here, okay? Creating a projection that looks like this, okay? And let's take a look at what it would look at theta equal to 45. If we rotate and take a projection at theta equal to 45, okay? So now I've rotated the detectors are now on this side here, okay? The X-rays are coming in this direction. The X-rays are coming in this direction, okay? And right in the middle here is where S equals 0. Going up this way is positive. Going this way is negative. And you see the projection is now at S equals 0, okay? See that? Now, when I rotate into theta equal to 90 degrees, what should happen? This projection should shift over this way, right? So let's see that now. Okay, and it does. Okay, you see it shift, now the projection, now the detectors are here, and the X-rays are coming in this direction. Okay, and as they go through the object, they create a projection on the positive side over here. See how it's on the positive side over here? Okay, so this is taking projections from a couple of different angles, okay? Now let's go ahead and create the full sinogram. Let's take projections all the way around it. So I'm going to go from theta, from 0 all the way to 359. So I'm going to take 360 projections all the way around it and plot it. Let's see what it looks like. Okay, so this is what it looks like. And this is, what do we call this image? A sinogram, right? So this is the sinogram, and you can see it produces kind of this sine wave, the object, by taking multiple projections and plotting the projections, stacking them up next to each other. Okay, so this is S detectors versus theta. So each projection at each theta is stacked up next to each other, and you can see what the sinogram looks like. Okay. Okay, now if we generate something a little bit more complex, okay, just create a image with three objects. Okay, so I have three different objects in this image. Okay, and they're all different shapes. And we actually looked at this image in the lecture. Okay, uh, so let's take a look at what the sinograms would look like. Okay, first, if I take a projection at theta equal to 0, okay, let me pull up that image. This is the projection at theta equal to 0, which means the detectors are down here. X-rays are coming from this direction and creating a projection like this. Okay, and it's all there's three objects, but they all kind of overlapping each other around s equal to 0, as expected, right? At theta equal to 90, they should show three different projections, right? Let's take a look at theta equal to 90. And it's as we expected, right? Now, with the detectors are now at theta equal to 90 degrees. X-rays are coming from this direction. This object produces this projection here on the negative side, and it's also brighter and taller because it's thicker, right? This thicker distance times the linear density makes it brighter. This one in the middle is a little bit off to the negative side, and then this one here is broader, right? And we can generate the full sinogram. So again, I will run it for theta equal to 0 to 59, 359. So it'll be 360 degrees all the way around. And this is what the sinogram of that looks like. And again, this is just a simple image, a little bit more complex. It has three objects, but you can see those three different objects and how they produce three different traces. And you could identify which trace comes from which object. Okay, but as you can imagine, the body, the human body, is way more complex. And so let's look at something a little bit more complex. We'll take a look at this sinogram. Okay, so this is a sinogram of something a little bit more complex. Comes a little bit harder to tell, but some obvious things happening out here on the edges. You can tell it's circular, but not perfectly circular. Okay. So that's a sinogram. Well, you can use again, the sinogram is using the radon function to plot all the projections next to each other. Okay, and we can use the inverse radon function to reconstruct the image using back projection. Okay, so if you recall the steps of back projection, where you smear the data back, assign an equal weighting to all the pixels that contributed to that projection, and then repeat that for each theta, and then add it all together, you can reconstruct the image. And this is what that object was. This was it's the Shep-Logan phantom. Okay. Okay, and now let me demonstrate a little bit how this might look for a larger study. This is an actual CT scan, okay? It's an actual CT scan that I'm going to take each sinogram, okay? Let's take a look at the sinograms. Okay, these are actual sinograms of the human body, okay? And I'll just cycle through them. So I wrote a little code to take each slice or each sinogram and reconstruct it, and then start putting it together, stacking it up into something called a hypercube. Okay, so let me show you what that looks like. So I take one, reconstruct it, and start stacking it up. Okay, let me show you what that's going to look like. Okay, so that's what I'm going to run this code, and it's going to and again, if you're interested in learning more about this code, again, uh, you could take my summer class. But see, I pull up a sinogram, then I do the steps of filtered back projection, and I reconstruct the image. This is what it looks like when it's reconstructed. Okay, I take a sinogram, reconstruct it. Then I take it and I stack it up into something called a hypercube. Okay, so this is the bottom part of the torso. You can see the lungs on both sides, the chest. You can see the ribs right here. Okay, and it's going really slow because I'm displaying every single image. Okay, uh, if I was running this for reals, I wouldn't display every single image. I would comment that part out of the code and it would run faster. Okay, so I'll just go ahead and abort this by pressing Control C, and that aborts uh, that code. Okay, because it will take too long to run uh, showing each image. So what I would do is I would comment out these uh, where I show the image every time, and then just run it, and you'll see that it runs a lot faster. Still takes quite a bit of time though. You see, it's on the seventh image, eighth image, ninth image, and there's I think there's like 480 or 460 sinograms. So it did 30 of them so far. Okay. Again, I'm recording the screen and everything. There's a lot of the computers actually doing quite a bit of work right now. So I'll go ahead and abort this. Okay. Let me pull up. something to write on. And I just want to explain to you real quick what is a hypercube. Okay, so an image, a 2D image is something like this, right? Has rows and columns. It's a matrix, right? And like I was saying, I take the first one, reconstruct it, and then I stack them up next to each other, and I create something called a hypercube. Okay, something like this, where the next image gets placed right behind it right here. Okay, and the next image gets placed right behind it right here. And I keep stacking up all the images, and then I can cycle through these uh, images and look through them. Okay, let me show you what that looks like. Okay, so we went through all the sinograms, reconstructed all the sinograms using the filtered back projection, and then we stack them all up next to each other so we can scroll through it. Okay, so let's see what that looks like. It takes a while for it to load. I'll go ahead and close Matlab, free up some resources on the computer. And as that's working, I want to bring up another concept. Okay, so again, you have rows or columns and rows, right? These are the columns. These are the rows, right? And this makes up the matrix of pixels, right? And so on one image, on a 2D image, you just have one pixel looks like this, right? But as you create this, as you start stacking them up, you start adding more, we create kind of a 3D volume. Okay, so and now we call it, instead of a pixel, we call it a voxel. Okay, so now we have a voxel. Okay, so if we include the image, the stack of images behind it, okay, I get a hypercube. Okay, and each pixel is now called a voxel. Okay, and let's see if this. Okay, this has loaded now. Okay, so here's all the reconstructed images. Okay, so this is a CT scan of the torso starting about chest height. Okay, and let me move up. Okay, so I'm cycling through. I'm moving up. Okay, here you can see some ribs. These are the two lungs. Okay, this is a vertebrae. This is his airway. Okay, as I'm moving up, this is his collarbone. Okay, collarbone. And as I'm moving up, okay, this is again his airway in his throat. Okay, and as I move up, this is his jaw. This is his bottom jaw. Okay, there's his airway. There's his nose. There's his eyes. Okay, so again, we stacked them all up and created this hypercube, which they call a study. Okay, and then we're cycling through those images. Okay, so I'm just going through them like this. This is his head. Okay, there's his brain. You can see the ventricles inside the brain here, and going all the way to the top, you can see the crown of his head. This is the top of his head. It's the very top of his head. Okay, so I'm gonna go back down. Okay, and so you can see how we've taken all these projections at all many different angles all the way around the body, and created these sinograms and moved down the body by imaging through slices going down the body, and then reconstruct all of these sinograms and then stack them all up next to each other to create this study. Okay, so this is a CT scan. Okay, so this is a CT scan of just this guy's torso. So in a CT scan, uh, if you break your foot, they're not going to image your whole body. They're just going to image your foot. So although they can image you can image the whole body. A lot of time, CT scans are just going to be the part that they're interested in. If they want to look at the head, they just image the head. If they want to look at the foot, they just image the foot. Okay, so this is here they just image the top of the torso and the head. Okay, so that's what that looks like. Okay, um, and remember, all of this comes from these sinograms. That all of this is what we just looked at, reconstructed. This is what a raw image looks like in a CT scan. Okay, and again, I'll remind you, this is the power of combining two important concepts of the hardware and the software, right? The software is the programming and the mathematics and the image processing. The hardware is the X-ray tube and the X-ray detectors and the design of the system. You need both, right? You need both in order to produce these images. Okay, so that's how a real sinogram looks like, and that's how you can reconstruct it. And let me now introduce you to mimics. Okay, so I'll open up mimics. And I'll just do a brief introduction. And like I said, what I'm going to do is I'm going to post a workbook online with step-by-step tutorials, and I'm going to post a CT scan, okay, that for you to work through, okay, and follow step by step and go through it at your own pace. But just briefly, I'm just going to show you an introduction, okay. So this is mimics. I've opened up mimics. Now let me open up a study, okay. So I'm going to open up a CT scan of the head, so of the skull. Open up a CT scan of the skull, and remember we have this hypercube, right? We have this um, study like this, right? We can look at it, we can slice it and look at it different ways, okay? If we look at it from the front, uh, uh, that's what we call the axial view, okay? So that's this one here if we're looking at from the front, okay? But if you look at it from, you can look at it you can slice it in another way. So you can slice it like this and look at it in this plane, okay? And that would be the coronal view, or you could slice it in this other plane this way, okay, and look at it in this view, and this is what's called the sagittal view, okay. So, and it's got them labeled right here. So this is axial, this is coronal, this is sagittal, okay. So here's the axial view, and again, if I just go up and down, and this software syncs them. So anywhere I click on here, so let's say, for example, I'm going to go up, okay, to this guy's eyes. I'm going to go back down to his eyes. His eyes are right there, right? Those are his two eyes right there. If I click on one of the eyes, it will move to wherever I clicked on the other views, okay? So there's one eye. If I click in the middle, it's going to show me the middle, okay. But remember, these are just nothing but stacks of images. They're all stacked up on top of each other, okay. So I can cycle, I can move up, okay. So here I'm moving up, okay. I can go to the top. This is the crown of his head. This is the top of his head, okay, right here in the axial view. In the coronal view, you can see that I'm at the top here, and in the sagittal view, you can see that I'm in the middle here, okay. So I'll just go back down somewhere in the middle, right about here, where his eyes are, maybe. There's his nose, okay. So that's the way this is oriented, and you can scroll through this on the, for example, in the sagittal view over here. I can do the same thing. I can scroll to the left, if I want to go to the left, and I can scroll back to the right. I can scroll to the right, okay. So I can slice this hypercube in different ways, okay. So these are like looking at cross sections, okay, of these images stacked up on top of each other, okay. Now remember what we did with thresholding in the beginning, right? We looked at, I'm going to reposition my cursor here in the center, okay. So I got the brain, and I got so the brain is soft tissue. I got the skull. The skull is obviously brighter pixel values, right? If we take a look at that and I draw a profile from here to here, okay, this is what that profile looks like. Again, it's plotting the pixel values, okay. So you see this peak here is the bright pixels of the skull right here. This peak here, let me turn off the lights so you can see. This peak right here, can you guys see that? Okay. That's the bright pixels of the skull right here, okay? So I could do thresholding on this and isolate the bone, right? So if I do simple thresholding, if I find a cutoff value somewhere right here, I could isolate just the bone, right? And I could do that for every slice. If I go through the whole image, slice by slice, and do this image segmentation by simple thresholding, I can identify all the bone and stack it all up together and create a 3D patient-specific geometry. So let me show you how to do that. Okay. Before I do that, I'll show you. You can also take measurements. Okay. Say you needed to measure the diameter of the head. Okay. You could measure the diameter like this. Okay. Let's say you needed to measure uh, the diameter of the eye. You scroll to the eye. Something of interest might be the optic nerve sheath here. The optic nerve sheath diameter, that's the optic nerve coming off the back of the eye. You could measure the diameter of that, but I'll just show you. So you just pick up the distance here, and you can measure like the diameter of the eye. Okay. So you can take different measurements and things like that as well. But let me show you if we do the thresholding that I was talking about on every single slice and just isolate the bone and stack them all up together. Okay. So I'm going to come here to segmentation and I'm going to create a new mask. Okay. And Mimix already has some predefined cutoff threshold values. And they have a minimum and a maximum. Okay. So everything between the min and the max here is what they identify as bone based on the Hounsfield unit. Okay, so the pixel value in here is given in Hounsfield units, right? Okay, so a typical bone usually has a Hounsfield units between this and that, and so I can actually move this. You can see if I drag this and go to the left a little bit, I am now picking up more than just bone. I'm picking up soft tissue. Okay, or if I come to the right, I'm picking up less bone. These are the brighter pixels. It's only getting the brighter pixels. Okay, and there's some predefined threshold values. So for soft tissue, I can click on soft tissue, and this is where all the soft tissue is in the image. But let's first just take a look at the bone. So I'll just pick the bone. So this is where all the bone is in the image. Okay, and I'll press OK. And I'll just rename this as bone. Okay, and I'll calculate a 3D part from it. So I'll calculate a part. So it's going to go through each slice and stack them all together. It'll take a second. So everywhere where it's green is where the pixel values were thresholded, right? Where it's not green is where the pixel values were outside of that threshold, or those cutoff values. So it's going to go through slice by slice and segment all of them based on the pixels, and then piece them all together in a 3D geometry. And it takes a little bit of time. And there we go. There is the 3D geometry of the bone in this CT scan. So you can see this guy's skull. Okay. Now remember, all of this came from taking X-rays at multiple angles all the way around the body, creating projections at multiple angles all the way around the body, and then reconstructing those projections using back projection and then stacking the reconstructed image all on top of each other. Okay, and so you can see the bone. Okay, there's several things you can do too. You can, you can cut it and look inside. Okay, you can look inside. Um, you can also reference the I'll press the space bar to make it a little bit bigger. Okay, but you can reference the planes that the coronal, sagittal, and axial planes as well. Okay, so these are where all these uh, pixels came from. You can see the other, and you can move through this, right? You can move you can move through this and look at it different ways. Okay, and you can identify. So I'll turn off those reference planes. Okay. So again, this is what you guys are going to be doing. This is mimics. Let me just show you guys real quick one more segmentation. I'll create a new map. Okay. This time I'm going to do soft tissue. Okay. And I'll press OK. And the soft tissue is going to be yellow. And I'll create a 3D part from that. And I'll say OK. So we'll be doing uh, through as you go through the workbook. Okay, so the workbook's gonna take you step by step. I'll upload a CT scan to Blackboard that you'll have to download. Pay attention where you download it. Okay, so you have to save as, and you'll probably have to extract it. It'll be in a zipped folder that you'll have to extract and then open it up in Mimics. Okay, if you get stuck, just send me an email and I'll help you through it. Okay. Uh, this is what you guys are going to do with mimics. I'm going to give you a CT scan of the torso. Okay. Going down to the hips, and you guys are going to isolate the bones in the hips and the spine, and start learning some basic image processing techniques. And any second now, it should produce the 3D mask of the soft tissue. Let's give it another moment. It's calculating the part still. Make a little bit longer because there's a lot more pixels to deal with. And I'm recording this my screen, so that could be taking some time too. Sometimes you'll have to be patient with this, especially as we work with larger data sets, okay, larger CT scans and things like that. Uh, you'll have to be a little bit patient. Okay, as that's computing, any questions? Okay, let's give this another minute or two. If it doesn't compute, then we'll just let it go. But if it does, let's give it another minute or two. Okay, it looks like it's about to do it. Okay, so this is the soft tissue. I press the space bar on that window and I can get a bigger view. You guys see that thing around his head? Any ideas what that is? That's just a foam pad to rest his head in. Okay, this might actually be a cadaver, um, and they got the head resting in a foam pad. This is a foam pad. Okay, uh, but again, you can still do the different reference planes. You can look at the reference planes here. Okay, and you can move those around. You can look inside as well. Let me turn off the reference planes. Let's do a cross section. Okay, if you want to look inside the brain, you can look inside. There's the brain. Okay, uh, so you can slice this up any way that you want. Okay, and look at it and from different angles and different views and things like that. Okay, so that's mimics. Okay, and that's what you guys will be working on Thursday. Again, it's going to be individual, self-paced, working through the step-by-step notebook that I post, and then we'll meet again as a class next Tuesday here. Okay. All right. So we'll go ahead and end there, and we'll see you guys next time.